Hello, my name is Natalie Williams, and today I'm presenting my lab on analyzing the Georgia Tech free rowing boat. So, firstly, I chose this lab because I'm on the Georgia Tech rowing team, and I am curious about the application and conservation of momentum, the center of mass, and Newton's third law with respect to my championship boat. So, the goal of the lab is to analyze the momentum of the boat in respect to the different pieces of equipment and rowers, specifically the oars, and apply Newton's third law that every action has a reaction. So ultimately, we will be investigating the oar itself and the work done by the rower. So here are some fundamental formulas and principles. Feel free to pause the video in order to take a look. But we'll be introducing a new concept today, which is defining the motion of the oar in relation to the boat with conservation of momentum. So as you can see, we have two separate formulas for elastic collision versus inelastic collisions. Elastic collisions mean that the overall change in energy equals zero. However, the motion of the oar going through the water is considered inelastic due to resistance from the water, which means that there's a dissipation of kinetic energy to the water as the system becomes the mass of the oar and the water being displaced. But due to limitations on this analysis, we will treat it as elastic instead for simplicity. So here we have the video for the tracker, um, which uses the initial conditions that the mass of the oar is 3 kilograms and that we're ignoring the overall resistance of the water. And as it can be seen, I use the length of our rowing shell as our reference for the distance of the oar. And here we can see the graph, which we'll be using for momentum in the other data. So here's my Globe script code. Here we calculate the momentum update to find the total momentum of the oar and subsequently the amount of work used to accelerate the oar through the water. However, this completely ignores the main resistance of the water, as this would be too complex for this particular lab. So here we have momentum update itself, and then on the side we calculate, here's the momentum update and the work applied here. So for the results, it was found that the average momentum of the oar and work applied by the oar was the following. So momentum update was 74.0741 kilogram meters per second, and the work applied was 914.495 joules. However, this is relatively low because we have not considered resistance of the water in terms of work applied, as there's probably more work applied in order to move the boat. So what other forces are not accounted for? So the way an oar works is that it's essentially a lever, as can be seen here. This is, this is a free body diagram depicting the oar. Rotating around what we call an oar lock, which means that torque is the main mechanic involved in power application due to the force being applied on the handle of the oar to the blade connecting with the water, pushing through the resistance of the water. Furthermore, the power applied is done by the rower moving their center of mass relative to the shell, so sliding up and down the boat, which is done by accelerating the legs and torso quickly. Unfortunately, the motion of a rowing boat is too complex to fully analyze, but it's kind of fascinating to just investigate it even on a surface level. Finally, what other factors are not being considered in the model versus the real-life boat, and how does this affect momentum? In rowing, there's no such thing as world records. There are only world best times because there are so many factors that can affect rowing, which means that each course has their own best time because every difference in circumstance makes a difference in the physical application of rower power to the water. So here are some different examples. Hull buoyancy. So the way we would display this is via a free body diagram, and it is basically how the boat sits in relation to the water, how deep it is in the water, which means more or less surface area of the boat is in contact with the resistance of the mass of the water, which kind of works similarly to a normal force in that you are on the surface of an object, except it's water, which has a different density. Then we have current, which is the force applied to the hull to accelerate or decelerate the boat, which depends on the potential energy and subsequent kinetic energy of the body of water, such as a river. Um, Typically, races are held on lakes for this reason because there is less potential energy for the water flow. Then there's drag, which is wind conditions, which can make the boat slower as you're fighting against the wind. Tailwinds are preferred because it's basically pushing the boat forward as opposed to holding the boat back. But also wind conditions are fought via technique in that you can lay more into the wind, which covers a greater or reduces the surface area that the wind comes in contact to. Finally, we have equipment mass. So lighter equipment is easier to accelerate due to less force needed to be applied by the rowers, but heavier equipment also ensures maintained momentum. So honestly, this is a preference based on the strength of rowers versus cardio. So thank you.